Sorry about that. Sorry, you can receive.
So thank you very much, everybody, to be here. We'll continue on Arctic River. This time, we're going to talk about the distribution of rare earth elements and their signature from the Mackenzie Delta to the abyssal Arctic Ocean. But to better understand what is the project here, what we want to do, well, first we need to talk a bit about the Mackenzie Delta. So it's a critical site if we want to study the sediment export to the Arctic Ocean, because it's the main sediment source to the Arctic Ocean. So we're talking about 128 megaton annually. And in the last 20 years, there was a marked export in particulate matter, marked increase in particulate matter export of about 50%. So we know that there is more particulate matter, but we don't know where it's going. We don't know what's the fate of it. And that's what we want to see. So we want to use tracers to know where this particulate matter is going to go. So to use tracers, well, we decided to work with a rare earth element. They are a series in the periodic table that comprise the lanthanide and scandium and yttrium, but for our work, we're only going to work with the lanthanides. And those elements, they're used in high-end technology, but also they're used as sediment tracers. And the reason behind that is they tend to stay together in the environment. They react in a similar way. They all have the same redox state. So all of them can be found in the trivalent redox state, but cerium can be oxidized in highly oxidizing condition, and europium can be reduced to cerium-4 and europium-2 respectively. They can exist in other redox state, but not in the environment, just to be clear. Another nice thing about them is in the environment, they tend to react in 3 different groups. So we can separate them in light, medium, and heavy rare earth element, and those groups will react even similar together. And also, because of the Otto-Atkins effect, they tend to vary in a C-tooth pattern, so we need to find a way to reduce this effect. So with that in mind, we decided to use those tracers to evaluate. So that's the project that we have. So first, we want to evaluate the usefulness of a rare earth element as tracer of the fate of sediment in the Arctic Ocean. So we're talking more on a spatial point. And then we want to assess change in the relative contribution of sediment source over time using this new tracer. So what it means is now we want to work also on a temporal point. So we have 2 different dimension that we want to study here. So to do that, well, first we need a lot of samples. So we went all around the Arctic Ocean, the Mackenzie region, the Meckler Strait, Barrow Canyon, Bering and Chukchi Shelf, up to the Emerasian Basin, and we took sediment cores to study what are the source of sediment there. So we went in the icebreaker, in the helicopter, or in boat, depending on the type of sample that we needed, and we took sediment cores. And as you may know, well, sediment, the deeper sediment is older, so we brought all the sediment and we cut it at every centimeter. That way, with each site, we have a spatial sampling, and then for each core, we have a temporal one. So we brought all the sediment, and then back to the lab, I did some sample treatment, then leach extraction, other sample treatment, and I did my analysis at ICP triple quad MS to produce signature. So signature is going to be really the key here that we want to use, and I'll explain a bit more what it is and how we can interpret it, so the rest of the work will be easier to understand. So a signature, well, first, when I took my sample and I did my analysis at the ICP, I had a signature like that. So we had the different rare earth element and the concentration, and as you can see, there is a big variation. So I did 2 normalizations. First one with the North American shale composite to eliminate the sawtooth pattern, and then I did another normalization with praseodymium to make all the sample, at about the same concentration, so we can easily compare different sample matrix and different overall concentration. Because what we want to see here on the signature is the relative concentration of the different group of rare earth elements. So if we look at this one, I'll explain to you what we need to see, and then it's going to be easier for you to understand the rest. So this is a signature in the Mackenzie region, and as we can see, there is a relative enrichment of medium rare earth element compared to the light one. And this is representative of those sites of the weathering effect and the source of sediment in the Mackenzie region. And it's like a fingerprint. Also, what we can see here is each line, it represents a different depth. So at every depth on that side, the signature is relatively the same. So what we can have from this signature is that there is an enrichment in medium rare earth element and that there's not a lot of change with time on that side. So we did that on every sample, every site. So we have a lot of qualitative data with that, with all the Mackenzie region showing similar signature. Or if we look more in the American Basin, we can see that, well, the medium rare earth element enrichment is really, really lower, but we have a really higher light rare earth element, and we have a cerium concentration that is an anomaly. And this can be due to the oxygen penetration in the sediment, which, as I said before, may oxidize cerium. So this can also have an impact. So we have all the data, but we wanted to be quantitative because with that, we cannot do that much. So what we did is we developed an index. So as I said, we want to see the relative enrichment of medium on light. So we did the ratio between the concentration of the medium rare earth element on the light ones, and we add an index. And then to better compare in a spatial standpoint, we use two end members. So we use the Mackenzie region and the American Basin, and depending on the similarity of or signature to one of those end member, well, we add a data. So I'll show you what it means on the map. So here we have the similarity index. A value closer to 1 signifies that the signature is closer to the Mackenzie region. And a value closer to 0 signifies that it's less similar to the Mackenzie region and more similar to our other endpoint, which is the American Basin. So as we can see here, without surprise, in the Mackenzie Delta, all the signatures are similar. Well, that's what we can we thought because it's the same sediment source and the same weathering process. But when we go a bit farther, that's where things get interesting. Well, first, what we can see is the farther we get away from the Mackenzie region, and the less the signature is similar. Again, it's something that we can, it's logical because, well, the farther you get away, the less the contribution of the Mackenzie region will be. But also there's some interesting thing we can see. For example, here in the McClure Strait, well, we're pretty close to the Mackenzie region, but we know, but the signature is really different. And we know that in the McClure Strait, most of the sediment come from surrounding island or drifting sea ice. At the same time, if we look at the Bering and Chukchi shelves, all the signatures are similar together, but dissimilar to the Mackenzie region. So again, they have similar sediment source. And lastly, if we look at the Barrow Canyon, we have two sides that are really close together, but we know that for BC6, most of the sediment may come from the Beaufort Gyre, which is a current going around here, and for BC4, it's just at the mouth of the Yukon River. So those two have different signature, even if they're close together. So all of this data, it can show us that the signature is a good indicator of spatial distribution of sediment. But now, as I said, we also want to know, well, can we see for temporal change? So we took the same ratio that I talked before, the medium rare earth element on light one, and we took it for every sample at every depth, and we did profiles with that. So what we can see here, well, we have the depth in the y-axis and the ratio in the x-axis. And the deeper we are, the older is the sediment. So for most of our sites, we're talking about 150 years. And for the Mackenzie region, it's a bit younger since there's a lot of sedimentation. And for the American Basin, we're talking about 10,000 years since the sedimentation rate is really, really, really low. So overall, what we can see is for, if we're talking about the Barrow Canyon, we can see that in the last 20 to 50 years, there was an increase in the ratio, which means that the medium rare earth element enrichment increase. And this could be due, as we said at the beginning, to an increase in particulate export from the Mackenzie. So it's a way that we can evaluate the change in sediment over time, sediment source. But we need to be careful because if we look at the Emergent Basin, we have a lot of change. But I want to remember to you that we saw a cerium anomaly. So since the oxygen may penetrate the sediment inside with low sedimentation rate and low organic carbon matter, well, it is a possibility that in those cases, there's going to be a redistribution of some of the rare earth element, and this may influence the signature. So in conclusion, we analyzed 226 samples across 21 sites, and we determined the rare earth element concentration in the Laval phase. And our index, well, they were correlated with what we can see on different studies that were done in the region. So we think that it's a good use for them. But we need to be careful if we're talking about millennia-long time scale because it can have important implication if oxygenic flux enter the sediment. So I would like to thank the community that helped us to take the sample, Professor Raoul Couture, who took me in his lab, Professor Serghei, who gave us some sample, all the different people here for their work with me on the analysis, and lastly, the different sampling team. And if you want to see the article, you can just scan this QR code. And thank you, all of you, for your time.
Thanks for a great talk there. Any questions from the audience? We'll take one quick question.
Thanks very much for a great talk. It's a really impressive data set. I'm just wondering two related questions. Do you have corresponding manganese and iron data that you can link to the cerium anomalies that you're showing?
Yes, we have.
Okay. And then the second question is, why did you decide to do some sort of extraction in HCl rather than a total digest?
We did both, and what we did both for some of the sites, and what we saw is that the Laval phase were the biggest contributor of the signature, and it was the one that had the most difference between sites, and for the total, the relative contribution was less interesting, so that's why. But good question, thank you.
Thanks very much.
Thank you so much. I'd like to welcome our next speaker, Sam Pwyer from University of Queens.
Sorry. Good morning, everyone. My name is Sam Poirier. Today I'll be talking to you about my work studying the impacts of permafrost disturbance on nitrogen cycling in the high Arctic. This work builds on previous work by Dr. Lafreniere revisiting two sites that were subject of study in 2012. So active layer detachments, or ALDs, are one of the most common forms of permafrost disturbance. They happen when the active layer, or the seasonally thawed layer, slides off of the permafrost, covering still frozen permafrost. These often happen during warmer seasons and after intense rainfall, when the active layer becomes saturated and heavy, increasing the frictional force needed to keep it in place. These disturbances strip away the top layer, the organic layer, as well as vegetation, exposing mineral layers and changing surface and subsurface flow paths. In 2007, Cape Bounty received a record amount of rainfall in the late season after a particularly warm summer, triggering over 700 active layer detachments in the West River watershed. 3 of these happened in the Ptarmigan catchment, affecting approximately 12% of its area. Active layer detachments are, of course, very important for nitrogen cycling. By removing the organic-rich active layer and exposing permafrost, they decrease the potential for biological uptake while mobilizing previously inaccessible mineral nitrogen. This is especially important in Arctic environments because they are so severely nitrogen limited. Most nitrogen input comes from wet deposition or internal processes like nitrification or mineralization. Nitrogen export in the Arctic is, of course, primarily driven by snowmelt, with a big pulse during the spring freshet coming from accumulated snow and surface leaching or surface soil leaching. After the active layer detachments of 2007, a 5-year post-disturbance study in 2012 found that ptarmigan exported 30 times more dissolved inorganic nitrogen than pre-disturbance and 27 times more dissolved inorganic nitrogen than an undisturbed catchment called Goose. Export of nitrate experienced the biggest change in the catchment, going from about 1% of total dissolved inorganic nitrogen to being over 20%. Prior to disturbance, these two catchments had very similar concentrations of nitrogen, as well as very low export of dissolved inorganic nitrogen through the season. There was also a seasonal shift from a snowmelt dominated to a storm flow dominated export of nitrogen. We're now revisiting these two sites to see if the effective disturbance can still be measured. So, as previously mentioned, our two sites are at Cape Bounty Arctic Watershed. These two sites were the same that were studied in 2012. There are two parallel catchments of similar size, both underlain by continuous permafrost. They have a similar change in elevation, making them ideal for the isolation or for isolating the effects of disturbance. As you can see here on the map, ptarmigan is outlined in orange and Goose is outlined in blue, ptarmigan being the disturbed catchment. And I'm going to try and follow that color scheme through the presentation. So everything in orange will be related to ptarmigan and blue to Goose. Just quickly before I move on, all the meteorological data and precipitation data were taken at the Camp Met Station there, the little triangle in the bottom right-hand corner. To measure discharge, everything was directed through cutthroat flumes that were instrumented with depth loggers, and then we calculated rating curves from manual measurements taken during sampling. Samples were collected in opaque Nalgene bottles twice daily during peak flow, and then down to once daily during base flow, and of course no samples when there was no discharge. Samples were kept cool until they could be processed and filtered in our infield lab, and then filtered samples were sent south to be analyzed at Queen's University. This past season was unusually cold and dry at Cape Bounty. We recorded one of the lowest maximum mean daily air temperatures in the past decade, with a high of only 9.8 degrees Celsius, compared to 2012, which had a maximum average daily temperature of 16 degrees Celsius. Only 28 millimeters of precipitation fell this season. That's 60% less than the 20-year average, and 19 millimeters of that precipitation came in one rain event in late July there. Hydrologically, this makes for a very simple hydrograph with a big peak during snowmelt, followed by a base flow in Goose, a short base flow period in ptarmigan, and then a prolonged period of no flow in ptarmigan. There was a brief return to flow in both catchments during and directly following that large rain event late in July, giving us a nice snapshot of storm flow conditions. Goose had a larger discharge peak as well as higher discharge through the season, likely due to its larger size. It also has a bit of a larger proportion of wet sedge meadow in the catchment, and it had a snowfield that persisted late into the season because of our low temperatures. Getting into some results, we have box plots of seasonal concentrations in both catchments. Just for some context, in 2012, ptarmigan's mean nitrogen concentration, or nitrate, concentration was 32 times higher than Goose, nitrate being the middle there. This year, it was only about double that of Goose. Nitrite on the left, concentrations were also elevated, possibly indicating higher rates of nitrification in the catchment. And then ammonium on the right, concentrations were lower in ptarmigan than in Goose, likely from less organic matter in the catchment, especially in the scar zone of the active layer detachment. This suggests, just quickly, that even 17 years post-disturbance, some effects of disturbance still remain in ptarmigan. Here's a seasonal breakdown for nitrite. We see early peaks during snowmelt, likely a remnant of incomplete nitrification prior to freeze up in the fall. Concentrations then decline over the season, indicating nitrification plays less of a role in late season export. Goose exported nearly twice as much nitrogen as nitrate compared to ptarmigan, the majority of which came during the snowmelt period. Even though concentrations were low, higher rates of discharge, of course, led to higher overall export. And that might have also diluted that concentration signal from goose. Given that nitrate is usually thought of as a pretty minor player in seasonal export, this points to a possible underappreciation of nitrite as an exporter of dissolved inorganic nitrogen in seasonal nitrogen budgets. Moving on to nitrate, 2012 data showed early nitrate peaks, which are more consistent with these sites across all the years we've studied. We observed late season peaks, you can see there in late June, that didn't correspond very well with precipitation events, which is the typical input of nitrate. They did correspond, however, to some increase in temperatures, suggesting that nitrate here may be derived from nitrification. Again, in contrast to 2012, we don't see those early season peaks. However, the cool temperatures of the season may have contributed to slower melt and lower nitrate concentrations early in the season. Export of nitrogen as nitrate was twice as high in goose than in ptarmigan, with fairly consistent concentrations in goose. Discharge was definitely the determining factor here. Even though it had lower concentrations, much higher discharge, much greater total seasonal export. Similarly, in ptarmigan, export was very heavily dependent on discharge. So it had a bit higher of a concentration, very high export early in the season. However, of course, because discharge stopped, export stopped as well. Looking finally at ammonium. Ammonium is the most variable. We didn't see the expected snowmelt peak again. Ammonium is the most readily taken up dissolved inorganic nitrogen species taken up by vegetation, that is. So typically you'd see the highest concentrations during the early season, and then when the onset of the growing season starts, you see a sharp decrease in concentrations because it's all being taken up and not making it to the watercourses. We didn't see that here. We see our highest concentrations later in the season. These peaks were actually aligned with some spikes in temperature, indicating they may be more derived from leaching and mineralization. Base flow was the dominant period of ammonium export in goose, suggesting low flow conditions still contribute significantly to seasonal export, especially it seems in cooler years because you're not getting the majority in your snowmelt period. Export from ptarmigan was more typical with high export during snowmelt, but in its short base flow period, export remained high, and this might be because of its low organic and vegetation cover, meaning it not as much as being taken up by vegetation. Finally, looking at total dissolved inorganic nitrogen exports for the season. Again, for a little context of the past, in 2012, ptarmigan exported 27 times more inorganic nitrogen than goose. But in 2024, goose exported 4 times more inorganic nitrogen than ptarmigan. A reversal in the trend. However, this reversal is definitely driven more by hydrological changes than in recovery of biogeochemical processes. Ptarmigan's dissolved inorganic nitrogen did still, however, include higher proportions of nitrite and nitrate, suggesting altered biogeochemical processes still remain even if export was lower. Since 2012, the ratio of ammonium and nitrate to the ratio of ammonium to nitrate and nitrite has changed in both catchments. In ptarmigan, nitrate to ammonium used to be around 1:1 in 2012, and this year it was closer to 1:4. And then in goose, the ratio used to be 1:25, that's nitrate to ammonium, and is now around 1:8. So an increase in the proportion of ammonium to nitrate nitrate to ammonium in ptarmigan, and a decrease in goose, potentially suggesting the recovery of some biological processes in the disturbed area. These pie charts also illustrate well the role that nitrite played in seasonal export. In both catchments, it played a larger role than nitrate. So quickly, just to summarize, ptarmigan still has a higher average concentration of all species of inorganic nitrogen. Nitrite played a much larger role in export of inorganic nitrogen than previously thought. Nitrate and nitrite still make up a greater proportion of dissolved inorganic nitrogen in the disturbed catchment than in the undisturbed catchment. Seasonal export of nitrogen is still heavily dependent on environmental factors that affect discharge and biological uptake. And lastly, we did not observe higher discharge or higher export of dissolved inorganic nitrogen in ptarmigan, the disturbed catchment, than in goose, the undisturbed catchment. However, this is probably driven by a cold and dry year, not a recovery of biological processes. Next, I'd love to incorporate some dissolved organic nitrogen values into this work. Issues with analysis have prevented me from doing that so far. And I'd also like to use some stable nitrogen isotopes as source tracers for that mid-season peak of nitrate in ptarmigan. I'd like to thank everyone at Cape Bounty, as well as Dr. Lafreniere and all of our funders. And I'll take a couple questions if we have time.
All right, thanks very much for that. Any questions from the audience?
Thank you. It was really interesting. I have just one small question about when you have your like your timeline with the concentration. Do you have an idea about the error bar? What would it be on those data? Because
on
the nitrate or nitrite or
I mean,
ammonia.
it varies between species, of course, but it's really quite low. I think I was getting like 0.01.
Which method are you using to do
so we're using a ion chromatographer.
Okay.
And I can tell you what columns and stuff we're using. But yeah, just standard ion chromatography.
Okay, thank you very much.
Of course.
All right, are there any more questions? One more back here.
Hi, if I understood it correctly, you had high nitrogen runoff that correlated with you correlated with temperature. It wasn't part of the high precipitation.
Yep.
I was just wondering whether permafrost melt could be a factor in that sort of thing.
Well, exactly. So we would expect that if you're getting those high peaks in concentration, that it's coming from increased thaw and then leaching from the surface of the soil. If it did correspond with a precipitation event, it would be more likely coming from runoff. So the other source would be, yeah, permafrost thaw there, for sure.
All right, thank you very much.
Thank you.
And our next speaker is Noelle Starling, and she is from University of Waterloo.
Shorter than our previous speakers. Back to the start. Spoiler alert. Sorry. All right, hello. Hi, my name is Noelle Starling. I'm from the University of Waterloo under the supervision of Dr. Philippe Van Capellen and Dr. Chris Parsons, and I'm here today to talk to you about some dammed nutrients. And by that I mean reservoirs and the impact they're having on phosphorus and nitrogen export across the Lake Winnipeg Basin. Now, I'm sure I'm preaching to the choir here when I present Lake Winnipeg as a major research and management priority. In the literature, it's been called both Canada's sickest lake and the forgotten Great Lake, which I think perfectly illustrates why it's such a research interest. It's a major fishery, an important habitat, a major recreational site, and an important water supply for the region. In Lake Winnipeg, the watershed is unique because of its prairie climate. It's a climate characterized by extremes. We see hot, dry summers, cold winters where snowpack is able to accumulate. And so 80% of the annual runoff arrives during the spring just due to that snowpack melting. The result is that there's very low biological activity during runoff. So our traditional BMPs based in vegetation uptake are less effective in this region. It also means that most of the nutrients being transported are in the dissolved fraction, as you have frozen soils and freeze-thaw to the detritus at the surface. Overall, this shapes a highly seasonal water and nutrient budget for the region. So as a result of the seasonal water budget, reservoirs have been an important water management tool in the region since the 1920s. There's 156 large reservoirs, that's a reservoir with more than 10 hectares of surface area, across the region. Most were constructed originally for a combination of flood control and water supply management, but many have later been constructed or retrofitted for hydroelectricity as well. Past research has shown that both globally and in this region, these reservoirs often have an impact of retaining nitrogen and phosphorus loads from downstream sites. So my research questions were, how are these reservoirs altering the flows of nitrogen and phosphorus in the watershed? I say flows because I'm looking both at the amount and the timing of transport. And what features of these reservoirs and their surrounding environment help us predict whether it will be more or less retentive of nitrogen and phosphorus? So in order to do this, we had to find sites where we had inflow and outflow monitoring of both periodic concentration data and daily discharge. So in the end, we found 6 long-term sites. These are sites with 10 years of approximately monthly water quality sampling. These are from federal, provincial, and municipal governments. And they were paired with Water Survey of Canada discharge monitoring sites. We also found 6 short-term sites that were previously published in a paper by Donald et al. In 2015 from Environment Climate Change Canada. These sites only have 3 years of data, but had excellent sample coverage, making them suitable for the study. So some of you guessed it immediately when I said we were looking for paired concentration and discharge sites, but I use CQ modeling in my work. So CQ stands for concentration discharge, and these use the relationship between the amount of a chemical of interest and how fast the water is moving to tell us about transport and load. So a positive CQ relationship suggests something is mobilized by runoff. It's from the surface soil. A flat or chemostatic CQ relationship suggests a large homogeneous source. This is often things supplied by the groundwater. And a negative CQ relationship we would call a dilution. So this is stuff like chloride, where you would have some available at the surface. It would be washed in during flow periods, but it would be diluted as your rainfall increases because it's a limited supply. The other interesting thing you can do with the CQ relationship is once you understand what the relationship is, you can use it to gap fill those monthly concentration samples based on the discharge because you know the relationship. So in order to do that, I use a model called WRTDS, weighted regression on time, season, and discharge. This was a method developed by Hirsch et al. At the USGS. And has been built upon in years after. And WRTDS is unique because it makes a specific CQ relationship for each day in your study period. And it does this by assuming that a day is more similar to another day if they are close temporally, if they are similar in discharge, and if they are similar in season. And so Zhang et al., who was a student of Hirsch, went on to propose that the B2 coefficient of this relationship could be used as a daily representative of the CQ slope. I mentioned earlier in my presentation that the nutrient and water transport in this basin is highly seasonal, so having a seasonal representation of the transport patterns is incredibly important in order to accurately reflect the conditions. So we used this model to estimate the amount of load of phosphorus and nitrogen flowing into the reservoir and flowing out of the reservoir, and this allowed us to calculate retention efficiency. So a positive retention efficiency, or a positive value indicates retention, a negative value would suggest enrichment. We also operated under the assumption that all area above the monitoring point provides equal amount of water and concentration, and this allowed us to correct for the unmonitored loads between inflow monitoring and the mouth of the dam, seen in green in my figure, and the extra monitored area between the mouth of the dam and our outflow monitoring site, seen in my figure in red. So I present to you the ugliest violin plot of my career, but I promise it's ugly with a purpose. So this shows above the red line, we have where retention is happening each year, and below the line, we have where enrichment is happening each year at all the sites in the study. So we'll start with nitrogen. Nitrogen is using that red line like a hopscotch rope. So this suggests that nitrogen retention and or enrichment is highly interannually variable. So on any given year, a site could increase the nitrogen load by 50% or decrease the outflowing nitrogen load by 50%. However, for phosphorus, we see that In almost all our sites, we have phosphorus retention between 20 and 90%. And this suggests that reservoirs are significant sinks for phosphorus and are retaining downstream load. We do have 2 sites that do show an enrichment trend. This is Bald Hill Dam in the Red River and Lac du Bonnet in the Winnipeg Basin. So this is interesting because there are only 2 sites outside of Saskatchewan River Basin. But overall, what we know is that these reservoirs are preferentially retaining phosphorus over nitrogen. Piece of evidence too. So we see that reservoirs suppress the CQ slope and the seasonal load. So remember that B2 coefficient I mentioned earlier? That is plotted averaged by month here for each site. And so what we see is that above the reservoir before you have, or above the dam before you have reservoir impacts, we see a seasonal cycle in the CQ relationship. So we have major runoff happening in the spring, and we move towards more chemostatic conditions, but still see a mostly runoff trend for both phosphorus and nitrogen. However, when you cross a reservoir, you push the outflows towards chemostasis, meaning that in the prairies, when we have that flush of nitrogen that arrives with the spring freshet, when you cross the reservoir holds that nutrient and then releases your concentrations at a more stable rate throughout time. If you were here yesterday and saw me speak in French, I likened it to a thermostat, creating stability in a fluctuating environment. We see a similar trend for nitrogen, but much less extreme. Okay, so if we put those 2 pieces, so phosphorus load decreasing more than nitrogen load and pushing towards stable release, we see an impact on the seasonality of the molar nitrogen to phosphorus ratio. So as you would expect, because the reservoirs retain more phosphorus, we see an overall increase in the nitrogen to phosphorus ratio. The figure I have here is delta molar entropy, so how much each month the entropy ratio is changing across the reservoir. We see the greatest impact of this change during the freshet. So normally we would expect during the freshet that your nitrogen to phosphorus ratio would drop as your amounts of phosphorus rise with the runoff. However, when you introduce a dam, you retain that. So we have an overall impact of seeing higher nitrogen to phosphorus ratios during that spring. We also see that some reservoirs are actually decreasing the molar entropy ratio by the time we arrive at late fall and winter. That's because, again, we've stabilized that outflowing phosphorus concentration. So instead of having sort of a push of phosphorus and a stable rate of nitrogen, we have sort of that winter and fall phosphorus sort of coming up to meet the nitrogen there. So this has major impacts on primary production in Lake Winnipeg and other lakes in the basin, and can be significantly important to the formation and shape of ecological communities in the region. So overall trends, this is when you take a photo because I'm about to summarize all the work. Phosphorus, the CQ slope changes by negative 0.58, and we see a 47% decrease in the load. Nitrogen, we see only a negative 0.18 change in CQ slope. That's because nitrogen transport is already very chemostatic in this region, and a percent loading change overall of -3, but very interannually variable. And overall, this increases the molar entropy ratio across the basin by 12 points. Photos now. So our question was, what factors of the reservoirs help us predict whether it will retain or release? So we compiled, I think, 36 potential factors that we thought maybe have predictive power, and we used an MR approach, so MR, maximum relevancy, minimum redundancy, in order to rank the factors. So what we see is that the inflowing CQ relationship, that B2 inflow, has significant predictive power over retention and enrichment. So that's really important because it tells us that if we can study the basin's CQ relationship, we may be able to estimate how retentive the reservoirs in that basin will be. We also see that upstream land use was a strong predictor of retention and enrichment behavior. I suspect that this is likely due to the impact that land use has on chemical speciation, but that remains to be verified. We also see that temperature is important, especially because we took annual average maximum monthly temperatures. So if the maximum monthly temperature was above 0, we averaged it for that year, and we used this as a proxy for the growing season temperature. And we saw that growing season temperature also had significant predictive power, especially in the case of nitrogen. We also color-coded these factors. So Anything pink is to do with the water chemistry, anything green is to do with the watershed, the environment, climate characteristics, and anything blue is really important because blue is reservoir characteristics. So this is anything that a potential manager or policymaker would have decision-making power over. So the age of the reservoir, harder to control, could potentially be impacted by dredging, the volume of the reservoir, the water residency time, how much the reservoir changes inflow variability relative to outflow variability. This is all manageable factors. So our next steps are applying these identified parameters to a GAM model in order to attain estimates of retention efficiencies for all the unmonitored large reservoirs in the Lake Winnipeg Basin. This would allow us to quantify basin-wide nitrogen and phosphorus loading and identify retention and enrichment hotspots, and estimate how overall change is happening to phosphorus and nitrogen across the Lake Winnipeg Basin. So quick summary before I let you ask questions. Retention or enrichment of phosphorus and nitrogen by reservoirs is annually and seasonally variable. Reservoirs attenuate seasonal variability of phosphorus and nitrogen concentrations and loads, and the inflowing CQ relationship, land use, temperature, and water residence time have potential to be predictive factors of retention or enrichment in the reservoirs. Overall, reservoirs are reducing the phosphorus and increasing the nitrogen to phosphorus ratios that are reaching Lake Winnipeg. Thank you so much. I would love to take questions.
Thank you very much.
Thank you. Any questions from the audience?
Great talk. Thanks very much. You showed a plot where some of the reservoirs were exporting phosphorus, and I thought that was kind of interesting and surprising. And just wondering, do you have a sense of those two weird reservoirs that were actually,
Yeah.
do you sense of what was driving that?
It's interesting. I don't have a sense of exactly what's driving it. I will say these are two fairly old reservoirs. They are also two reservoirs outside of the Saskatchewan River. So 10 out of the 12 sites I have in the study are within the Saskatchewan Basin. Bald Hill Dam is in the Red River, which we know is a significant phosphorus supplier. So it's possible that this dam is just getting overrun with that phosphorus load. In the case of Lac du Bonnet, it is in Lake Winnipeg, so it's a much different environment. It's a forested and area with a lot of wetlands. So I suspect that is likely having an impact. It's very climatically and environmentally different than the other reservoirs in the study.
Thank you.
Thanks. Are there any other questions? All right. With that, I think we will move on to our next speaker. Thank you
you
very
so much.
So our next speaker is Jafar Safari from the Toronto Metropolitan University. Welcome on stage.
Good morning, everyone. My name is Jafar Safari from Toronto Metropolitan University. Today, I'm excited to share our recent work on chloride load modeling with key predictors and machine learning. This work carried out with collaboration with Professor Claire Oswald, Professor Christopher Wallen, and Bill Thompson. Also, this work carried out with close collaboration with Lake Simcoe Region Conservation and Authority, and also this project supported by the Ontario Ministry of the Environment, Conservation and Parks. Chloride contamination is a pressing environmental issue in cold climate regions such as southern Ontario. Road salts such as sodium chloride are heavily applied for winter road safety, but frequently flush into nearby streams and lakes. This leads to increased chloride concentration, especially in the urbanized watersheds. Now, in many cases, chloride concentration exceeds the Canadian chronic exposure guideline of 120 milligram per liter and approach the accurate threshold of 640 milligram per liter. Elevated chloride disrupts aquatic lives, alters lake stratification, accumulate over time. Monitoring data highlights the urgent need for better understanding and management. By increasing the complexity of the environmental problems, machine learning algorithms can be considered as a reliable tool for modeling the nonlinear process and to improve the accuracy of the developed models. This study aims to improve the chloride load modeling by addressing the critical gaps in the modeling and also provide the more accurate models. This study captures the nonlinear dynamic in chloride transport by integrating the several models such as GAM and advanced machine learning algorithms such as random forest and its hybridized version with harmonious search algorithm. Different important variables such as seasonality, stream flow, baseline time are incorporated in the model to enhance the accuracy. Also, the interaction between the seasonality and stream flow are analyzed, and finally, spatial mapping identifies sub-watersheds that exist the chronic and accurate threshold value of the Canadian exposure guideline for targeting water quality management strategies. For complementary and comprehensive perspective, please see Professor Kirsten Wallen's presentation this conference about the a conceptual model on chloride dynamics in the Lake Simcoe watershed. He also served as principal investigator of this project. Our study area is Lake Simcoe watershed located in southern Ontario with 2,634 kilometers squares with 20% lakes, surface, 18 rivers, and over 4,000 kilometers of tributaries. Major land use in this watershed is agriculture, but rapid urbanization significantly impact on the water quality of the watershed. We use chloride concentration and stream flow data from 80 monitoring stations across the Lake Simcoe watershed that provides comprehensive spatial and temporal coverage. Land use change from 2000 to 2018 in the Lake Simcoe watershed shows the rapid urbanization and changing the land use type to urban and road land use, especially in some watersheds such as East Holland and Barrie Creeks. Also, while declining in the agricultural land use, especially in some watersheds, sub-watersheds such as Hewitt Creek and Oxbridge Brook. This shift toward urbanization significantly impact on the chloride loading and also change runoff dynamics. The chloride concentration data used in this study are collected by graph sampling method that provided the discrete measurement and also it rather than the continuous modeling that provide a large gap, more than 90% missing chloride load data. So this data gap hinders the accurate temporal trend analysis and make difficulty in the modeling. So robust data imputation techniques are needed to overcome this problem. In this study, we integrated several hydrological and temporal variables to calculate the chloride load. We incorporated the long transform stream flow to account for the flow variability, base flow fraction to consider subsurface flow, day of year to reflect the seasonality by roll salt application and snow melt. And also we incorporated time to detect the long-term trends due to urbanization, climate change, and human activities. This predictor can capture the nonlinear dynamics of the chloride load transport across space and time. We applied three models. Our first model is the generalized additive model as a non-parametric extension of the generalized linear model, and also we applied two machine learning techniques. First one, random forest. This is the ensemble form of the decision tree, and also its hybridized version with harmonious search algorithm. Random forest is very sensitive to the hyperparameters such as number of trees, minimum leaf size, and number of predictors samples at each place. So harmonious search algorithm can optimize the standalone random forest and improve its accuracy. The comparison of the model shows that the harmonious random forest with harmonious search algorithm outperforms its alternatives with higher coefficient of determination and then the lower root mean square and Cocky information criterion. Its hybridized version improves the random forest model by a factor of 20 to 40% in terms of root mean square, while improves the performance of the GAM model with a factor of the 30 to 60% in terms of the root mean square error. comparison of the models shows that while the results of the hybrid models close the base fit line, but there is a significant underestimation and overestimation for the gamma and random forest models. Also, the comparison of the time series of the discharge and chloride load shows this significant seasonality in the chloride load data, and while they elevated baseline for the urbanized watersheds. Variable importance analysis shows that the contribution of each predictor is significantly varies by sub-watershed characteristics. Day of year or seasonality is dominant variable for the urbanized sub-watershed that shows the strong seasonal effect of the road salt application and also rapid runoff over impervious surface. The log transform stream flow is found as a more dominant variable in the agriculture and rural sub-watersheds, such as Beaver River, that shows the hydrological variability derives chloride dynamics. Base flow fraction is also important. Some watersheds, such as Beaver River, that shows the importance of the groundwater in chloride flow release and storage. Time also emerges as an important variable in some stations that shows the long term of the chloride accumulation and climate variability. 3D surface plot shows the interaction between the stream flow and seasonal variability. Generally, chloride load increased by stream flow in late winter and early spring, that when the chloride load flush into the water bodies. For example, in a urbanized area in the East Holland station, there is a strong seasonality in this station, and amount of the chloride load reached to the 400 ton per day. In the another station, for example, in the Maxinang River, this is agriculture sub-watershed. In this sub-watershed, are more influenced by stream flow rather than the seasonality. There is a weaker seasonality in this station. Partial effect of the time and chloride load shows the steady increase in the chloride load due to their human activities, road salt application, and also climate variability. There is a drop in 2008 and 9 that can be linked to the change in the road salt maintenance, but it needs deep investigation to better understand the reason for that. There is a sharper trend for the urbanized sub-watershed as well. In these maps, the evolution of the chloride concentration in the Lake Simcoe watershed for 2000 to 2008, 2013, and 2018 are shown related to the chronic and acute chloride value. It shows that while in the 2002 amount of the chloride concentration is low, in 2013 and 2018, the chloride concentration value reached to the acute threshold value of the 640 milligram per liter. As a conclusion, our hybrid random forest model hybridized with harmonic search algorithm outperforms GAM and standalone random forest model. Seasonality as found dominant variable in urbanized, suburbanized, and roads dense sub-watersheds, while stream flow and base flow are find the important variable in the agriculture and natural heritage area. Time also emerged as an important variable in some stations that shows the long-term impact of the chloride accumulation and also urbanization. The spatial and temporal analysis shows that the amount of the chloride concentration in hotspots in urbanized and road dense stations past the chronic and acute concentration. This study and the results of this study supports the sustainable salt practice and long-term monitoring to manage chloride pollution in freshwater ecosystem. As an ongoing project, based on findings of this project, now we are working on the inlet chloride accumulation to assess the long-term impact beyond watershed loading. Thank you very much. I'll be happy to answer any question.
Any questions from the audience?
Thank you for your presentation.
Thank
You mentioned early on that a lot of the monitoring data or data sets don't contain chloride data directly, but they often do contain electrical conductivity, which is related to the chloride concentration. Have you looked at that? Maybe also as a validation for your modeling?
Yeah, that's a very good question. I didn't mention this point in my presentation. Actually, I calculated chloride load data from chloride concentration. But in the final analysis and evaluate the model based on chloride load, and finally to understand what happened in the waters in terms of the chloride concentration, I use the volume weighted discharge to change the chloride load to chloride concentration. Yeah, it means at the first step, I filled the data gaps by chloride load, and finally I changed the chloride load to chloride concentration to understand what's happening in the watershed. Thank you.
Additional questions? I have one, as someone who grew up in Southern Ontario and has watched from afar how your winters are changing. So as you look at the lake impacts and as Southern Ontario sort of changes in its experience of the 0-degree isotherm and you get shorter and shorter winters, when is chloride not going to be a problem and how do we account for that in some of our decision making? So at some point you're not going to have winter. Is that 2050? When is that?
Sorry, I couldn't understand.
At some point, you're not going to have road salt application because you're not going to have much snow.
Yeah.
So how do we build that into some of our decision-making and modeling processes?
Yeah. It's a very good question. Actually, there is a limited data about the amount of the road salt application in the different regions. So we tried in another project that the Professor Swalt conducted. We tried to get the amount of the road salt from different municipality, but only from the in this area only we found the few amount of the road salt data from the Newmarket municipality. This needs the huge amount of the data and working close with the municipality to get their amount of the road salt to find the relationship between the amount of the road salt applied and the amount of the chloride concentration and chloride load in the streams and lake as well. But this is a very challenging problem now in this project. Thank you.
I agree, and I think across a lot of the issues we work on, it's those small areas where a little bit of data would go a very, very long way. I have one other question, and then we'll go to our last speaker, which is living here where we don't use much road salt, but we still see chloride changes. How important is water softener salt?
Yeah, it definitely impact of the water quality amount of the road salt, but this is for this investigation to better understand your question could be considered in our future investigations. Thank you. Thank you.
Okay. Hello, I would love to present our next speaker, last but not least, Serghei Bocaniov. Am I saying that right? Bocaniov, okay, from the University of Waterloo.
I think we can start, yeah. Okay, in this presentation, I would like to draw attention to two invisible but potentially important sources of phosphorus loads to lakes. These are the shoreline erosion and aquatic food web. Both can be very significant in some lakes, but they are not parts of the routine monitoring programs. For that reason, so they are not accounted for, and they are not used in the present-day lake mass budgets. And as an example, I will use Lake Erie to illustrate that. And just a few words to introduce Lake Erie. Lake Erie is a very large lake. Just like to imagine the size, if some of you is from Saskatchewan and they know Saskatchewan has a very big reservoir, it's called like Lake Diefenbaker. So if you think about Lake Erie, so think about system that's 60 times larger than Lake Diefenbaker by area and by volume. And Lake Erie, what is important for Lake Erie, because that it has 3 distinct basins, and those 3 basins, so they're determined in terms of the phosphorus loads. You can see here how the water moves in this lake. So like more phosphorus loads to the western basin, less to the central basin, and least to the eastern basin. And because of this, so they have different productivity. They also differ in terms of the mixing in thermal regime, and you see those gradients in depths and the gradients in productivity in those gradients west to east. So what is the issue with Lake Erie? Because Lake Erie was very polluted in 1960s and 1970s, but in the early 1970s, the human interventions took place and the nutrients were reduced mostly from the point sources. So the lake recovered, you can see in the 80s and also in the beginning of the 1990s. But then, surprisingly, from late 1990s, the lake started to show signs of increased eutrophication symptoms. And those eutrophication symptoms are numerous, but the most important are the toxic, massive, harmful algal blooms, cyanobacterial harmful algal blooms, and also increased size and duration of hypoxic and anoxic areas in the central basin. And you know, in the central basin, so the hypoxic zone, hypoxic is a low dissolved oxygen zone near the bottom, is the largest of known on the freshwater systems. So the reason for this was not very clear. So we decided to use the phosphorus mass budget to understand what might be behind of that eutrophication symptoms in the lake. So it was, we decided to build up on the most recent total phosphorus budget that published in 2023 in ecological informatics. And we decided to update this budget with existing TP, like existing mass budget, with the observed sedimentation burial rates of phosphorus. We also want to, and those previous budgets showed that the sum of all outputs, so they were like larger than the sum of all inputs, showing some kind of deficit. So we decided in the study to estimate the amount of total phosphorus loads from the shoreline erosion to see if it's able to meet that difference, to balance that difference. And finally, we want to estimate the amount of phosphorus incorporated in the lake food web, because lake food web is some kind of behind of very important lake processes, but the people, they don't know how much phosphorus in this food web. And I will use those like abbreviation TP, stand for total phosphorus, and P for phosphorus in my presentation. So these slides illustrate the TP budget, existing budget for post-2000 conditions. And on the left side, you can see basic specific budgets. On the right side, you can see whole lake budget. You can see all inputs of the phosphorus. You can see outputs of the phosphorus. So number 2, this is a barrel of the phosphorus. And you can see in the middle, like how much phosphorus in the water column. The issue with that budget was that each basin shows some kind of deficit. So the outputs exceeds the inputs. And the total deficit for if you look at the whole lake differences, so approximately 3,500 of metric tons is additional loads are needed to balance all inputs with outputs. And also for this budget, the sedimentation barrel rates were based on the modeling studies, and modeling studies, so they were not like actual what was observed. And at that study, we didn't account for all P in the water column. We only consider phosphorus, how much in the water phase. But we know that aquatic food web may contain lots of phosphorus. So we decided to update this budget with those. So this slide showing how we estimated the observed burial rates of phosphorus. So what we did, so we went to the, on one of the lake cruises, we took sediment cores, we can see on the sides, from 3 sedimentation basins. We took from the deepest side of those basins, then we sliced the sediment cores into 1 centimeter increments, and we estimated the age of these increments and also TP content. On the left side, you can see example from the TP content from 2 profiles from the central basin. You can see this orange one and the blue from the central basin. So here you can see years, and this is TP content. And we took for this average value we estimated for the time when we estimated our budget, we took the average value, and we did the same for the Western Basin, and then determined by the very detailed, from the results from very detailed study of how much sediment accumulation, annual sediment accumulation in each of the basin. So we multiplied them, and we determined how much phosphorus is removed from the lake on the annual basis. And just to remind you about the aquatic food web determined the relationship between producers and consumers. It determined the nutrient, it's responsible for the nutrients, for example, phosphorus and energy flux from all over the system. And it might accumulate lots of phosphorus. And to estimate those, like how much phosphorus in the food web, we use data from the lake-wide monitoring surveys, and we estimated the biomass and then the dry biomass, and finally the how much phosphorus in this for phytoplankton, zooplankton, fish, and zoobenthos. So this is slide representing our results. Just focus on the left side on this for now. So what slide does it show? It shows like 3 basins. It shows like inputs of phosphorus, like outputs of the phosphorus. And this is like outflow from advective outflow, and this is from turbulent mixing, and how much phosphorus is burial, and this is observed values. And inside there is boxes for the food web, so like phytoplankton, zooplankton, fish, and zoobenthos. And look on this. So if you look in the Western Basin, if you look how much phosphorus in zoobenthos, it's much more than in phytoplankton. And the same if you look, for example, for the Eastern Basin here, you can see also there is much more phosphorus in zoobenthos than in the phytoplankton. So it's approximately 14 times more. It means that the food web is benthic food web in those basins. And it's completely different because in 40, 50 years ago, all 3 basins, they possessed the planktonic food web. This is some kind of simplified slide from the simplified version of the previous slides. All the food web is merged into one value. So you can see also fluxes to the lake and out of the lake. And here, like how much phosphorus like in the lake, on the great area, in the water column, and how much phosphorus in the water in the food web. And you can see much more phosphorus in the food web than in water column. And if you can see the difference now between all the outputs and inputs, you can see that for the lake whole budget, it's approximately 6.7 thousand metric tons. And of known processes in the lake that only like shoreline erosion it's a process that can provide sediments of this magnitude. So we want to estimate this. So we sampled some bluff material from the bluffs, and 98% of the Lake Erie coastline is made of the coastal bluffs. So we measured like 3 sites. We measured different location of phosphorus. We measured concentration, and we determined the mean, for example, concentration and median TP concentration. And for our study, we used the median concentration. So this is like from the detailed study of the shoreline of the fine sediment material, annual inputs of the sediment material to the lake. You can see shoreline provide the majority of this material, and yeah. So we multiplied that proportion of the shoreline erosion from the bluff materials by the concentration, and we determined that shoreline erosion is potentially able to provide 5,000, 3,000 metric tons. It's about 80% to cover all the difference, but the rest can be by the dredge soils. Dredge soils, if they're in the river deltas and marinas, so they clean the sediment, they move and dispose them in the lake. So, and if we use very conservative value for those, for the river sediments, it's about 1,000. So we make it, so if you can sum up, it's exactly coming to 6,700 metric tons. It's able, so shoreline erosion plus dredge spoils, so that sediment that moved from one location to another location from river deltas is able to cover that deficit. So this is some kind of the new updated budget. So you can see on the right side that is simplified. This is more detailed budget. So again, if you sum up all and add, for example, shoreline erosion, you can see that red values. So it closes the budget. So it's like it can like meet the deficit. So now the budget, TP budget, is closed. So what is the conclusion from this study? So there is more phosphorus incorporated in food web than in water column, and this is important when there is perturbations of the different levels. So the phosphorus can add to the water column. There is Western and Eastern Basin has benthic food web, while Central Basin have pelagic food web. And contemporary burial rates of TP are large, to 12,700 metric tons. And they're not that large, so they were the same, almost the same as they were like 40 years ago. And to balance all TP outputs with all inputs, additional inputs of 6,700 metric tons is needed. And the shoreline erosion and lake sediment dumplings, like two processes, are able to provide the same amount of phosphorus. And with that, I want to finish my study and thank you for your attention. Yeah. Thank you.
All right, thank you. Questions from the audience?
Hi, that was a great presentation. Thank you for sharing that. So I'm sorry if I missed this, but is essentially if we're able to reduce the amount of landslides and shoreline erosion, would that stabilize and like reduce the amount of eutrophication within the lake itself?
Yes, exactly.
Okay, and this is outside of the scope of your project, absolutely, but I know that there's been some really interesting engineered practices to try and reduce the impact of erosion and landslides on Lake Erie. In your personal opinion, you might not know this at all, but do you think that those will have a significant impact on reducing the loads to the point that eutrophication might be reduced a decent amount?
So this is yes, but it needs some kind of special attention, special approaches, but it's possible to reduce. So we need some kind of more knowledge, more like studies built, because it's also coastal erosion. We need some kind of engineering project to decide like where we can put those structures. And many structures exist. So the humanity has this very long experience how to reduce the coastal erosion. But unfortunately in Lake Erie, in the northern shore, we need more actions in that direction. If we want to reduce eutrophication, we need to pay attention to the watershed nutrient loads, but also pay to the shoreline erosion.
Thank you.
Thanks. Any additional questions?
Yeah, this one.
As well about that erosion, is that caused by human activity of some kind? Like would natural vegetation be stabilizing these banks normally, or is this a process that's been ongoing for a long time?
So this is very natural processes because the shoreline erosion in the freshwater, they are much larger than in the ocean. For example, in the ocean, you have tide that moves sediment like back and forward. In freshwater, it's not like this. So the shoreline erosion is much more higher. It's natural process because those bluffs, so they're made of highly erodible material that left after the glacier retreated. So this is purely natural process. Of course, the humans can contribute because, for example, they have infrastructure, they have roads. So that's something that overburdened the bluffs if this like too heavy, because bluffs consisted of several lenses of different material and some of them clay, and there is also like groundwater flow. So if it is something like, vibration and other, they can disturb. But I would say that more than 95%, it's a natural process, and we can handle this. We can just address this with proper engineering approaches.
Thank you.
All right. It is one more question before lunchtime.
Thank you very much. How did you date the deposits?
We use lead 210 and also cesium.
Okay.
So, but mostly it's lead 210.
And what model did you use for the age depth modeling?
So we did do it directly in our lab. So it's all got other labs. So we did all the chemical analysis and others, but that is demand specific knowledge.
Oh, okay.
And we have this isotope lab that based on the commercial.
understand. Okay, thank you.
So we prepare all the samples, gave to them, and from the field, and they just. So all everything else was made by us, except that.
All right. Thanks everyone for attendance to the morning session, and we look forward to seeing you in the next 2 sessions on this topic. Big thanks to the speakers who kept on time and did really great jobs, and enjoy your lunches, everybody. We'll see you soon.